To find the amount of work done in an object, you use this general formula, which is W equals force times displacement. If you imagine a box and it's sliding along the ground, and it's being pushed at an angle like this. Let's say after a bit of pushing, you manage to move the box over here. This distance is the displacement, and whichever component of force is parallel to the displacement, that is the force used in this equation. Now, if we assume this displacement is the x-axis, then this component that's parallel to the displacement is found with f cosine. That means another way to write this equation here is work equals force times distance cosine. And the angle you would take whatever this angle here is. Let's go through an example, and in this example, force is being applied in the direction of motion. So you're pushing a wheelbarrow, okay, this is you. And it is full of soil. The force being applied is in this direction, which we'll label with F, and the displacement is parallel. Let's say you push it with a force of 60 newtons, and it moves 100 meters forward. How much work did you do on this wheelbarrow? So because the force is in the same direction as the displacement, we don't have to use cosine or anything like that. We simply say work equals Fd, which is equal to 60 newtons times 100 meters. And the answer, you get 6,000 joules. In the standard SI system, which is used globally in science, joules, which is denoted with J, is the unit of measurement for work done. So 6,000 J. Let's go through a conceptual example this time. Imagine a lady, and she's standing here in the park on a nice sunny day. She's holding her baby, and let's look at the forces acting on the baby. There's the force of gravity, and to counteract gravity, there's the force being applied by the mother, holding the baby up. How much work is being done? There's actually zero work being done because there's zero displacement. The mother's not moving. Now, what if the mother starts walking forward this way? So the displacement would be this way, but the force being applied is going up. So that means the work being done on this baby is still zero. And here's why. We know that work is equal to F times D times cosine when there's an angle. The angle in this situation, which is always relative to displacement, is 90 degrees. And cosine 90 is equal to 0. The force is being applied perpendicular to displacement, it's not parallel. So there's zero work being done. Okay, let's go through a proper example now, a proper problem. Imagine a child sitting in a wagon. And this wagon here is being pulled by a father. There's a child sitting in the wagon, like this. Now the father is pulling with a force of 70 newtons. And he's pulling at an angle of 48 degrees. They keep on walking for another 122 meters. But that's not all. The road is very bumpy. So there's also the force of friction, which is 35 newtons in the opposite direction, so this way. How much work is being done by each force? So first, there's gravity and there's the normal force, but they're doing zero work because they are perpendicular to the displacement. What about the amount of work being done by this force, the pull of the father? Okay, let's solve this. So the work done by the pull, which we'll label WP, is the force of the pull times displacement times cosine of the angle. So that would be 70 newtons times 122 meters times cosine of 48. 48 being taken from here. Put this into a calculator, you get 10,900 joules. So that's the amount of work being done by the force of the pull. How about the amount of work being done by friction? So let's label it as WF, the work of friction. And this is equal to the force of friction times displacement times cosine 180. And we get 180 because here's the force of friction, right? And relative to the displacement, it's at an angle of 180 degrees. And cosine 180 degrees is equal to -1. So when you have a force acting in the opposite direction of the displacement, then this force is doing negative work. It's doing work against motion. So let's plug in our values. The force of friction, 35 newtons. Then displacement, 122 meters. This gives you -4,200 joules of work. Now, how do you find net work? So the total amount of work being done on this object. All you have to do is add up the amount of work being done by each force. This is 10,900 joules minus, because it's negative, 4,200 joules. And the net work being done is 6,700 joules. Here's the second problem. So imagine a Kung Fu master, and he has to walk up this mountain every day, carrying water on his shoulders. He's a Kung Fu master, so he holds 50 kilos of water on his shoulders. He has to climb a height of 100 meters. Now let's solve for three values. First is the work required by the man. Second is how much work is gravity doing. And last, we'll find the net work being done on the water. So because work is force times displacement, to find the work being done by the man, we need to find how much force he's using. So the water is 50 kilos, right? And let's draw a diagram. This is the water. These are the two buckets of water. And the water is at rest on the shoulders. There's the force of gravity pulling it down, which is 50 times 9.8. And this is 490 newtons. That means to keep it on his shoulders, he is constantly using a force of 490 newtons. Okay, cool. Now we know how much force the Kung Fu master is using, which is 490 newtons. How about the displacement, which is here? We're on an incline here. It's not a straight path. So let's use this formula. Work is equal to FD cosine. Now what I'm about to show you here is quite interesting. Look at D cosine. Now we're going to use this angle here. And if you look at cosine, the definition of cosine is adjacent over hypotenuse, which is height over displacement. If you multiply both sides by D, then you get D cosine equals height, which is 100 meters. That means we can plug in height for D cosine, which will give us work equals force, so 490 newtons, multiplied by height, so 100 meters. This gives you 4,900 joules of work being done by the Kung Fu master. So that means when it comes to work being done, what matters is the elevation, the change in height. The angle doesn't matter here. So if he were to lift water straight up for a height of 100 meters, he would be doing the same amount of work. Next, we're going to solve for the work being done by gravity. Let's draw a diagram. So this is our displacement, right? It's his path going up the mountain. We have the force being done by the Kung Fu man to hold up the water. And we have the force of gravity pulling down the water. And since gravity is not working parallel to the displacement, we need to use this formula, which has cosine. However, if we went and solved with this F times height, just like we did in the last example, we would get the same answer, which doesn't make sense because gravity is pulling in the opposite direction. So your answer would be negative. But let's go through some math so you can get a better, deeper understanding. Let's see what angle gravity is working at relative to the displacement. If this is theta, then this is also theta, which means this angle across here is theta. Then this inside angle is the angle that gravity is working at with displacement. Since this straight line angle would add up to 180, then this part of the angle here would be 180 minus theta. And cosine of this is equal to negative cosine. That's because of the trig identity. So if you haven't learned a lot of trig, don't worry. Just know that this is a trig identity and this simplifies to this. So now you have negative cosine. That means your new work formula is work being done is equal to FD cosine, but it's negative. And let's label the G for gravity. So work being done by gravity. So work being done by gravity is height. And the force here is mg, which is the force of gravity. That means the work being done by gravity is simply equal to mgh. And in this situation, it's negative. So plugging in our values, which is 50 kilos of water, 9.8 acceleration due to gravity, and 100 meters of height, then we get negative 49,000 joules, which, if you notice, same magnitude of work being done by the man, 49,000, but it's negative the other way, which perfectly balances it. How about the net work being done on these buckets of water? We just have to add up all the work being done by each force, which is the force of the Kung Fu Master plus the force of gravity. If you remember, it's simply 49,000 joules minus 49,000 joules. So the net work being done on the water is 0. But even though that the net work being done on the water buckets is equal to 0, the Kung Fu Master is still doing his 49,000 joules of work as he climbs up this hill. Now, everything I've done today has involved work being done by a constant force. But what if your force is varying, so it's changing throughout? Well, if you look at a graph, and let's say this is the force being applied in newtons, and this is the displacement, and it changes. The total work being done is the area under this curve, which requires calculus. So I'm not going to cover that today. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.